Okay, good morning, everyone, and welcome to the IFIMAC+ICMM joint seminar series on condensed matter. It is my pleasure today to introduce our speaker, María José Martínez-Pérez, Pepa. Pepa is an experimental researcher on different fields, such as superconductivity, magnetism, and quantum computation. She obtained the PhD in the Universidad de Zaragoza in 2011, where she worked on microsquid susceptibility of molecular qubits. Then she made a first postdoctoral stay in the NEST laboratory in Pisa, where she worked on quantum heat transport in superconducting circuits, and a second postdoctoral stay at the University of Tübingen in Germany, where she worked on nanosquids made of high critical temperature superconductors. Since 2017, Pepa is back in Zaragoza with a permanent position as a right senior researcher, and she is now also distinguished researcher at the Instituto de Nanociencia y Materiales de Aragón. Let me also mention that Pepa has received several prestigious prizes for her work, such as the Prize Aragón Investiga in 2017 and the Royal Physical Spanish Society Prize for Young Experimental Physicist in 2020. And recently, she has been awarded the ERC Starting Grant Project that she will start next September. As I said, it's a pleasure to have Pepa here. Today, she's going to tell us about NanoSQUID magnetometry of multi-shaped individual nanoparticles. Before giving the floor to Pepa, let me remind you that during the talk, your microphones will be muted, but you can make questions by writing them in the chat. And at the end of the talk, there will be more time for questions, so you can use the chat or raise your hand, and then I will unmute your microphone so you can ask the question yourself. Well, Pepa, thank you very much for coming, and the stage is yours.
Thank you, Isabel. So good morning to everyone. Thank you very much for being interested in my work, and thanks especially to Isabel for counting on me and also for her nice words. So as she said, my name is Pepa Martínez, and since few years I'm working back in Zaragoza in this recently formed INMA Institute, the Institute of Nanoscience and Materials of Aragon, which is the result of the joining of two older institutes, the ICMA, which was a joint research institute from CSIC and the University of Zaragoza, and the INA Institute from the University of Zaragoza. We are now all together in this INMA. Okay, here you can see our new logo. And today, as she said, I will show you some results that we have been obtaining when investigating small magnetic systems using NanoSQUID magnetometry or susceptibility. Okay, let me start by thanking all the people that has contributed to this work, especially people from my group in Zaragoza. We are called Quantum Materials and Devices Group. We joined together also quite recently, just 3-4 years ago. Also other people from my institute and the clean room in Zaragoza and the University of Zaragoza, and especially my collaborators from abroad, especially those in the University of Tübingen. Okay, so this is a brief outline of the seminar. I will start with an introduction, telling you why I am interested in the characterization of small magnetic objects and how I perform this characterization. I will speak in particular about squids. That's my topic of research, and a bit more in detail about why VCO nanosquids. Okay, and finally I will show you number of measurements that we have been performing in different small magnetic objects that you will see cover a really broad range of sizes and shapes. Okay, so let's start. As I told you, I'm interested in the study of small magnetic systems, and in particular in the study of those mechanisms that led to the reversal of the magnetization. Okay. Depending on the size, the number of atoms composing the system, and also their shape, this process can take place through different mechanisms. For instance, if we think of relatively large or mesoscopic or even larger magnetic bodies, normally what happens is that the magnetic moment reverses through the formation and move of magnetic domains and domain walls. If we reduce further the dimensionality and the size of our objects, we can find, for instance, a nanodisk, so a system that is reduced to the plane, being almost two-dimensional, and having some boundaries, like for instance in a disk where magnetic vortices can be stabilized. Reducing further the dimensionality and the size, we can deal with nanowires, where also the formation and move of domain walls takes an important role, but also for even smaller particles, we can find non-coherent or coherent rotation mechanism. Finally, if we go even farther down to the quantum realm, we find what are called single molecular magnets, so small magnetic molecules or even individual spins, where quantum phenomena usually play a fundamental role through quantum tunneling or quantum superposition. The study of all these different phenomena can be performed, for instance, through the study of the magnetic hysteresis curve of the system. Here you can see three examples. For instance, large objects where usually the formation and move of domain walls is the main mechanism, usually exhibit these typical peaks, or typical steps in their hysteresis curve. When we go to smaller objects where the particle is said to be in the single domain state, so all magnetic moments are almost always collinear between them, okay? One finds these typical square shape hysteresis curves. And finally, when quantum effects start being an important mechanism in the reversal of the magnetization, for instance, in magnetic molecules like iron 8 or the very well-known manganese 12, one finds these typical steps that are not due to the formation of domains, but to the tunneling of the magnetic moment corresponding to the different states that are quantized, okay, and this quantization becomes apparent experimentally. So since these mechanisms are so interesting and also interesting for applications, there have been, of course, since many years ago, many researchers interested in the development of magnetic characterization techniques. I have summarized here some of them, okay, according to three characteristics that I consider are especially important. First of all, of course, the magnetic sensitivity that you can see here in units of the Bohr magneton, okay? This M should be the Greek letter mu. Of course, the more sensitive the sensor, the better. Okay. Also important is the spatial resolution, because we are ideally want to distinguish small regions of magnetization, especially when doing microscopy, but also to distinguish different regions, like for instance the domain walls or vortices or skyrmions, etc. And a third characteristic that is very nice is the time resolution. This is so for magnetic processes, magnetic phenomena usually take place in extremely broad ranges of frequencies, okay? From very slow processes like what happens in the slow relaxation of superparamagnetic particles, up to extremely fast processes, like for instance magnetic excitations in domain walls or in spin waves. One technique that is very oftenly applied to the study of these systems is Kerr microscopy, MOCE, okay, that, as you can see, offers the largest time resolution. Is probably the technique offering the largest time resolution, okay? However, it lacks a bit it offers not so good magnetic sensitivity or spatial resolution. Additionally, it is not so easy to apply this technique at very low temperatures or at variable temperature. Another very interesting technique is Hall magnetometry that offers intermediate values of sensitivity spatial time resolution, but being not so good in terms of sensitivity. In terms of sensitivity, one of the most interesting techniques is nanosquid magnetometry, okay? Being close to the more sensitive techniques, as far as I know, that exist, that are based on the use of quantum properties of atomic point defects, like nitrogen vacancy centers in diamond. And nanosquid magnetometry, as I told you, will be the topic of this seminar. Okay, in this next slide, I wanted to show you to compare typical hysteresis curves obtained with these three different techniques that I've mentioned: Moche, Hall, and microsquid magnetometry. This is a Moche curve obtained for this iron. I think it was this iron nanowire here that you see at 45 degrees with respect to the substrate. As you can see, the noise to signal ratio is not so good, and please keep in mind that these measurements are usually obtained after integrating over many cycles. Okay. Secondly, we have these Hall measurements. Okay, where you see some hysteresis curves obtained at different temperatures. These measurements are really beautiful because they were obtained measuring just only these 4 three-dimensional iron cubes that you see here. Okay, there is a fourth cube below this graph. Okay, as you can see, Hall does offer the possibility, of course, of working at variable temperature and also under the application of very large magnetic fields. And finally, I wanted to show you these measurements. These are also really nice measurements performed in the mid-90s by Versdorfer. Versdorfer, who was the person who really pioneered this field of nanosquid or microsquid magnetometry. Okay, this is a typical hysteresis curve of particle where a vortex state is stabilized and annihilated. Okay, it corresponds to this tiny cobalt particle of just few 100 nanometers in diameter. Well, nanosquids, as I said, is the topic of this seminar, so I wanted just to remind you briefly how does a squid and a nanosquid work. Squids are the result of two phenomena. First, the quantization of the magnetic flux. Since the phase of the superconducting wave function describing a superconducting material must be single valued. Okay, this fact makes that the flux threading a superconducting loop okay, can be only described in integer numbers of the flux quantum. And secondly, the Josephson effect. A Josephson junction, as you know, is a weak link between those two superconductors. This weak link can be made of any non-superconducting material, like an insulator, a normal metal, or a constriction. The Josephson effect tells us that there is a relationship between the phase difference between the phases of the two superconducting condensates and the maximal critical current flowing through the junction. Okay, as a consequence of these two phenomena, one finds a typical interference pattern of the maximal critical current that flows through the squid as a function of the applied magnetic field. That means the flux that threads this loop. This phenomena occurs in full analogy to what you find when you make the typical experiment in which coherent light goes through a double slit, and you find bright and dark bands as a result. Okay, so this but itself constitutes already a magnetic sensor. Here you can see an example of the current voltage characteristic. So you current voltage your device, or you current bias your device, and you measure the resulting voltage. Once the maximum critical current is reached, a voltage develops and the system starts to dissipate energy. This maximal critical current is a function of the externally applied magnetic field, okay, being phi not periodic. This could be already used to measure magnetic properties, because one could measure at every point a current voltage characteristic and determine the maximal critical current. This is, however, not convenient at all from an experimental point of view, because you should perform this measurement at every point. What we normally do is to current bias the device at a current slightly above the maximum critical current, so that the device always works in the dissipative regime, and there is always a voltage, okay, that can be measured. And of course, this voltage will also depend on the flux threading the loop, okay, being also, of course, phi not periodic. So most of you have for sure worked with squids when characterizing magnetic materials, especially with commercial magnetometers. Here you can see an image of a typical squid from the company Quantum Design that many of you will for sure know. These devices usually work in the following way. You have one pickup coil circuit that couples the signal of your magnetic sample and is then later inductively coupled to your squid. Okay, this is made in this way so that the squid can be well shielded from the externally applied magnetic field that you need to excite your sample, because squids are superconducting and they don't like to be operated in magnetic fields. These pickup coils are usually also designed in a radiometric way, okay, as first order or second order radiometers, so to be insensitive to this externally applied field. Okay, this scheme is, however, not the best idea in order if you want to exploit the maximum of your sensitivity. If you want to exploit the sensitivity of the squid, you need to locate your particle directly in the squid. That's what Bersdorfer did, pioneering this field, okay? If you do so, you will find that your sensitivity depends only on two factors. First, the intrinsic noise of your device, okay? That depends only on the quality of your junctions and especially on the inductance of your device. The smallest the inductance, the better. That means that making your squid smaller will also reduce the noise. And second, the coupling factor that simply tells you how well your magnetic sample is coupled to your device. If you are working with small magnetic objects, you will also need your squid to be as small as possible to increase this coupling factor. That means the smaller the squid, the better. Okay, in this slide, I would like to summarize some of the measurements that my group and other groups have been doing along these years using nanosquids. Nanosquids have been developed by many different groups, but really there are very few examples, as you will see in the literature, that really apply these devices to the study of interesting problems in magnetism, okay? So as far as I know, there are only these ones that I am showing you here. First of all, of course, we have to start with Bersdorfer, who pioneered the field and performed the vastest amount of magnetization measurements using nanosquids and microsquids. These squids were based almost in niobium and aluminum and constriction-like junctions, okay? A second very nice example was, can you see schematized here, are these susceptometers. These are not magnetometers, but susceptometers, okay? These were made of niobium and developed by Ketchen and Avshalom in the late 80s and 90s, okay? In this case, the Josephson junctions consisted of insulating materials, SIS junctions. Secondly, we find this other family of susceptometers being very similar to those developed by Ketchen, okay? These were developed in my group thanks to the collaboration of the PTB in Berlin for studying magnetic molecules at very low temperatures, okay? We can also find this also a nice example in which niobium squids based on normal metallic junctions have been applied to the study of magnetic reversal mechanism in nanowires. This squid here is particularly nice because it consists of 3 orthogonally located loops that would allow in principle to measure the 3 orthogonal components of the vector magnetic moment. And finally, let me highlight this really nicest example of nanosquid that was developed for performing squid microscopy by the group of Eli Tseldov in the Weizmann Institute in Israel. It is, as far as I know, the smallest squid that exists, consisting of just a few 10 nanometers in diameter loop, okay, of niobium and mostly lead, a pattern on the ape of a quartz nanopipette, okay? This group has been using, and some other people coming from this group have been using this squid for studying very interesting problems like abrikoso vortices in superconductors, also reversal of magnetization in nanowires or magnetism in two-dimensional gases. So why are there not so many groups applying nanosquids to the study of small magnetic materials? Well, probably, maybe the reason is the following. As squids are superconductors, they are not so happy to be operated in under large magnetic fields and in large temperature ranges, which is normally what you need in order to perform magnetic characterization. Well, let me now just move to the main part of the presentation. Is where I will tell you a little bit about these YBCO NanoSQUIDs that we have been working with. YBCO is in principle a very nice material for the development of nanosquids because it's a high DC superconductor. So it will allow ideally operation upon large magnetic fields, and it is superconducting up to temperatures of 80-90 degrees. The problem is that patterning very small Josephson junctions down to the nanoscale or microscale is quite difficult with these materials. These materials are very anisotropic and their transport properties depend dramatically on the quality of the crystal. That also has a nice consequence for us, and is that grain boundaries between two crystals having different orientations exhibit Josephson behavior, okay? And that's how we fabricate our nanosquids. I will show you that in this slide. We start with a bicrystal substrate of STO, in which we have grain boundary. Then a layer of YBCO is epitaxially grown on top of it. In this way, the grain boundary is transferred to the YBCO layer. And finally, we cover this substrate with a thin layer of gold. Okay, I will tell you later if you like why this gold is important. We later pattern our nanosquids by using focus ion beam milling, leading to the formation of a nanoloop interrupted by the two Josephson junctions, as you see here, okay? This is a same image of a typical device, okay? Additionally, we pattern a small constriction here that allows us to flow a modulation current here through, okay, that can couple a net magnetic flux through the nanoloop. This is very useful for characterizing the devices, but also to operate them at an optimum working point. Since the response of a voltage response of a nanosquid, of a squid, is phi periodic, this constriction allows us to operate the squid in a flux lock loop mode, so at a fixed flux position, okay? Josephson junctions are here, lying perpendicular to the substrate, and a magnetic external flux can be applied in parallel to the substrate, so to influence our magnetic particle understudy, but not coupling any flux to the loop, neither to the junctions. So, as I already said, these devices are able of working under the application of large fields. This is here you see the maximum critical current, the modulation of the maximum critical current obtained at 0 Tesla and after the application of 1 and 3 Tesla. Okay, these fields are extremely large if you think you are working with a superconducting nano device. Okay, it's really a very, very large field, and still the modulation of the critical current is only slightly degraded. Of course, they are also able of working up to large temperatures of 70-80 degrees and also down to very low temperatures, okay? Finally, thanks to the small size of this nanoloop that yields extremely small inductances of just a few picohenry, we also obtain extremely low values of the flux noise at large frequencies, okay? We obtain values of the order of 50 nanophenot per square root of hertz. This noise is also is very low noise, okay? It's of the order of the best flux noise that you will find in the literature, for instance, for the squids developed by Elit Seldov for the squid on tip. This, together with the small size of the device, yields a very interesting spin sensitivity of only few Bohr magneton per square root of hertz per hertz. And just to finish, let me remind you that as squids are based on Josephson technology, these devices are in principle able of operating up to very large frequencies, okay, of several gigahertz or even terahertz. Okay, let's just now move to the last part of the presentation, where I will show you many measurements, okay, performed using particles covering a really broad range of sizes and also shapes. Let's start with nanodisc. So almost two-dimensional object with some boundaries, okay? Before doing so, let me introduce you what a vortex, magnetic vortex state is. In conventional bulk magnetic materials, the resulting ground state, the state of the object, will be given by the competition of a number of energies. You have on the one side the magnetocrystalline and exchange energy that tends to align magnetic moments parallel. In the case of magnetocrystalline anisotropy, parallel to some preferred axes, and in the case of exchange, parallel between them, for instance, for the case of a ferromagnet. And on the other hand, you have the magnetostatic or shape anisotropy. This energy tends to minimize the amount of stray field created by the magnet, okay? To reduce this shape energy, as you know, magnetic domains are formed. The size of the domain wall separating these two magnetic domains is usually given by the ratio between these two energies, the magnetocrystalline and the exchange energy. If the particles are smaller than the domain wall, particles are usually said to be single domain or almost single domain. But what happens when this magnetocrystalline anisotropy is negligible? Well, then the final state will be only given by these two main contributions. Of course, there are more contributions, but for understanding what I'm going to tell you next, these two are enough. Okay, in this case, you can really very easily, intuitively understand what the ground state of a particle will be. If you think of a very long particle like being almost one-dimensional, you will have all magnetic moments pointing parallel to the axis of the particle out of plane. Imagine a large, very large in-plane bidimensional material, you will have all the magnetic moments lying in plane. What happened in between for a, let's say, mesoscopic, almost bidimensional object? Well, usually what appears is a vortex, magnetic vortex, in which magnetic moments curl around the boundaries of the disk and point up or down in the center, okay, in order to satisfy also the exchange energy. These vortices do contribute also to magnetization reversal, as you can see in this video here. If your particle is saturated, for instance, at negative fields, and you reduce the field, at some point the vortex will be nucleated. Okay, this vortex will move depending on the direction of applied magnetic field up again, up to the point where the particle is saturated, and then back, and another vortex will be nucleated and move through the particle, okay? Well, these nice structures are very nice for applications because they constitute 4 state logic units, and they are also nice because they exhibit a number of interesting excitations at high frequencies that can be used, for instance, for creating spin waves or fabricating spin torque oscillators, etc. So we wanted to see whether we are able of studying these objects using our nanosquids. This that you see here is a particle fabricated in our clean room, consisting of permalloy with dimensions, as you see, of almost 600 nanometers in diameter, okay? And this, what you see here below, is the hysteresis curve that has been obtained by means of numerical simulations, okay? Experimentally, using our nanosquids, we find this kind of hysteresis curve that, as you can see, are remind quite a lot these numerical simulations and make us confident that we are stabilizing, nucleating, and annihilating magnetic vortices here in the squid. As you can see, these measurements can be obtained at a really broad range of temperatures, up to 60 Kelvin. This corresponds, let me remind you again, of measurements performed on one individual magnetic disk, okay? One nice thing that we can do with this disk is to control their circulation. Vortices can circulate clockwise or counterclockwise. To see this a bit more easily, we can fabricate a tap disk, okay? So a disk where the radial symmetry is broken. And if you think about that a bit in detail, this that you see here is an experimental measurements, and these here are numerical simulations. You are able of nucleating a clockwise circulating vortex or a counterclockwise circulating vortex, depending on which field you are nucleating the vortex. Okay, if the field is positive, what corresponds here to the red color, that means the magnetization going to the right is along the applied field, you will nucleate a clockwise vortex, and the opposite will happen if your vortex is nucleated at negative fields. Okay, they tell us that we can choose the circulation of our vortex, but we can also prove that this is that we are able of doing so, and to verify that experimentally. How? Since the annihilation field of the vortex depend on if you have a counterclockwise or a clockwise vortex. Okay, this can be seen in this figure when we compare a complete hysteresis loop in red, where the vortex that is being annihilated here comes from a counterclockwise vortex, whereas in the black curve, the vortex that is being annihilated here comes from a clockwise circulating vortex. As you can see, this there is a measurable difference between these two ones, thanks to the high sensitivity of these devices, okay, that allows us to verify the circulation of our vortices. Let's now reduce slightly the size of our objects and the dimensionality. Let's go to one dimension, studying nanowires. Okay, here you can see a set of 5 nanowires that were grown by means of focused electron beam in dust deposition of cobalt, leading to these nice three-dimensional structures going out of the plane. This technique is very nice, but it usually yields structures having very low metallic content. So our colleagues wanted to study if they could enhance the content of cobalt by an annealing procedure in which they anneal these nanowires at higher and higher temperatures, up to 600 degrees, to see whether this increases the crystallinity and the amount of cobalt. We measure these nanowires using our NanoSQUIDs, individual nanowires. Okay, these are some example. My mouse is not working very well. Well, these here are some hysteresis curves obtained at 4 Kelvin for individual nanowires annealed at different temperatures. The first thing we could tell is that the purity of these composites indeed increased. We could tell so because we can estimate the amount of magnetic material in our measurements by comparing the total signal captured by the squid with numerical simulations. As you see here in these numbers below, the purity, this P, of these composites indeed increased up to almost 100%. These numbers are very nicely agree very nicely with experimental measurements performed by electron energy loss spectroscopy. Okay, you can compare these purity values with those obtained by this technique here below. Sorry about my mouse, but it's not working very well. There were much more things that we could tell from these measurements, but I don't want to go too much in detail about that, but let me just mention that we could also verify that the anisotropy and therefore probably the crystallinity of this composite was being increased with annealing temperature. Okay, this was also verified by these high resolution TIM images that you see here below. This first picture here corresponds to the not annealed nanowire, where you can see that the structure is almost amorphous, whereas the nanowire annealed at the largest temperature exhibits these very nice Bragg diffraction peaks that correspond to a very nice crystalline structure. Okay, let's go down to even smaller nanoparticles. And in this case, we wanted to understand a bit more which factors determine the ground state of magnetic materials when they have intermediate sizes. Let me explain this a bit more in detail. This is a phase diagram showing you the ground state of particles of this shape depending on their thickness that you see here on the horizontal axis and the radius that you see here in the vertical axis. For very, very, very thick particles with a small radius, that means nanowires, you will find an out-of-place single domain. So a nanowire with the magnetic moment pointing along the z-axis. For thinner particles with larger radius, that means, for instance, disks, you will expect to have a vortex state as the only possible stable state of the particle. For very small particles, you expect the typical in-plane single domain particle. So single domain particles. But what happens here in the border, in the frontier between these two regions? To understand this, we fabricated a number of particles that you can see highlighted here. P1, P2, and P3 exhibited single domain behavior. This is proved by this quasi-square or almost a square hysteresis scores measured with the nanosquids that you can see here. Let me here highlight that these particles are now extremely small, okay, having magnetic moments of just 10 to the 6 Bohr magneton. But what happens with particles lying here in this purple area? Well, here we found signatures of vortex nucleation, but what we needed to prove is that the vortex is indeed the ground state of the particle. Okay, we verified this by electronholography, where the presence of a vortex is really evident, but also our measurements performed at variable temperature allowed us to verify the formation of vortex states, and also that these vortex states are really the ground state of the particle. Okay. Estimating the values of the energy barriers separating this vortex and the single domain states, thanks to the temperature dependent measurements, we could verify that at zero applied magnetic field, the ground state of the particle corresponds to a vortex state, with the single domain state being metastable. This is important because these particles are probably the smallest particles in which a magnetic vortex has been ever stabilized as a ground state. And let me now just move to the last part of this presentation, in which I will tell you a little bit about measurements performed with the smallest objects, okay, that with magnetic molecules. The study of these magnetic molecules is better performed not using magnetometry but susceptometry. Okay, we are interested in studying the spin dynamics of these molecules, and for this purpose, magnetic AC susceptibility offers much more information. Susceptibility is the derivative of the magnetization against the field, and has two components, one going in phase with the externally applied oscillating magnetic fields, that is the real phase, the real part, and one going out of phase with the externally applied oscillating magnetic field, that is the imaginary part. These quantities tell us much information about them, also the mechanism leading magnetization reversal. For instance, in the case of particles blocking their magnetic susceptibility, okay, one expects the presence of a peak in the imaginary part and a dip in the real part. This is so for the particle is able of following the externally applied magnetic fields. That means flipping its magnetic moment at the rate of the external magnetic field at low frequencies, but at larger frequencies it is blocked, it is not able of doing so. This process here can be done classically over the energy barrier created by the anisotropy, but also through quantum tunneling of the magnetization. Okay. So these experiments were performed with niobium microsusceptometers that I showed you in the beginning, developed thanks to the collaboration of the PTB, that consists of these two main circuits. A first primary circuit creates the externally applied oscillating magnetic field, and a secondary circuit catches the signal of the sample. It's proportional to the susceptibility of the sample. This circuit is inductively coupled to the nanosquid, to the microsquid in this case, okay? Well, here you can see a very nice measurement obtained with manganese 12. Manganese 12 is the archetype single molecular magnet that you can think of. It consists of 12 atoms of manganese, antiferromagnetically and strongly coupled between them, okay, giving rise to a total spin equal to 10. Here, relaxation can occur at different frequencies depending on some structural properties of the particle. Here you can see, for instance, an experimental measurement obtained with a small crystal containing two species. The fast relaxing species relaxing at frequencies of almost 1 megahertz, which is really high, and a slow relaxing one, relaxing at frequencies of a few hertz. Okay. Well, we have been applying these subceptometers to the study of many different single molecular magnets, putting special emphasis in the study of interesting candidates for quantum computing, okay, for encoding quantum bits. If you want to implement quantum bits, it is a bit easier if you focus on simpler molecular magnets, not manganese 12 that consist of 12 manganese atoms. But ideally, you prefer having simpler molecules consisting of, for instance, one individual atom, as this family that you see here. In particular, I wanted to show you these measurements performed with gadolinium ions that are encapsulated within these polyoxometallate cages. You have, in both cases, you have one individual gadolinium atom, but what is different is the polyoxometallate cage surrounding it, okay? As you can see here in the susceptibility measurements, the dynamics becomes completely different, okay? This one is much more isotropic, leading to these much faster relaxation rates. Okay, these particles, these measurements allowed us to, for instance, give the conclusion that this gadolinium tungsten 30 molecule would indeed implement a very interesting quantum bit for quantum computing application. Okay. Another interesting example, another measurements we performed were performed with this protein that you can see here. This protein is called ferritin. It's the protein that delivers iron within the organism of living beings. And it's an interesting one because using these susceptometers I showed you in the beginning, David Avshalom and Ketchen claimed the observation of quantum coherence. It's the largest particle in which this claim has been made, as far as I know. We apply a very interesting technique that is called deep nanolithography to deliver monolayers of these proteins above the surface of our sensor, okay? This can be verified in this AFM image when you see that the particles are indeed being arranged in a monolayer. Our measurements down to very low temperatures evidence that the properties of the particles of the proteins are kept down to very low temperatures, showing this supermagnetic blocking of the susceptibility as they do at when you measure a bulk sample. And now, just to finish, the last example I wanted to show you is this very nice molecule called Dysprosium 2, in which we find two Dysprosium atoms arranged in a way that they align antiferromagnetically between them, but being non-collinear. Okay. This arrangement makes this molecule a very interesting candidate for implementing a quantum CNOT gate. A CNOT gate is that flips the state of a target qubit, but depending on the state of the control qubit. This is possible thanks due to the fact that this asymmetry makes all transition in this molecule distinguishable. So one can choose the transition that one wants to promote. Okay. These particles were also delivered thanks to deep nanolithography, forming a very thin layer of just 5 molecules, and our measurements also show us that the properties of the particle of these molecules remain unchanged, okay, when compared with measurements performed in bulk samples. Okay, this is very nice because it tells us that these molecules still work as a CNOT gate when deposited in surfaces. Okay, so now I have finished my presentation. Let me finish by reminding you what I have shown you today. It's about the development of recently developed YBCO NanoSQUID sensors, okay, that are very interesting because due to their large sensitivity and also to the fact that they can operate upon large magnetic fields and broad temperature ranges, and niobium squid microsusceptometers developed thanks to the collaboration of the PTB. These devices can be applied, as I show you, to the study of many really different properties of magnetic small objects. Okay, I am now working in the increase of the frequency operation of these devices. This will be something really nice. If you remember, sensitivity of these squids is optimum at large frequencies, and thanks to the fact that these squids can indeed operate at such frequencies, will be very nice to apply them to the study of high frequency spin dynamics in topological magnetic textures, like for instance magnetic vortices. Okay, and this is all. So I thank you for being here, and I'm open for questions now.
Thank you very much, Pepa, for this wonderful talk. So please, if you have questions, write them in the chat or raise your hand. I think now you should be able to unmute the microphone by yourself. Now I think you are able to. So there is a question by Herman.
Hi, María José. Thank you very much for this nice talk. I mean, when you measure your susceptibility using this nice magnetometer which you are showing there, do you access the quantum properties of the particles, or
yes,
what
sure.
is? I mean, because. Okay, please go ahead. Yeah.
Yeah, indeed. Yeah, indeed. For instance, in these measurements here, what you are seeing is okay. What these peaks tell us is that the paramagnetic moment is being blocked, but at lower frequencies, okay, what we also demonstrated that this process of thermalization of the spin with the thermal bath. That's why the spin is following the magnetic field, because it follows the Curie law, is taking place through a quantum process. Okay, we could demonstrate that by comparing the expected relaxation times from a quantum process compared to the classical relaxation mechanisms like Orbach processes or the direct process.
But
yeah,
still,
sure. This also I forgot to highlight that, but these measurements, as you can see here, are performed in a dilution refrigerator. This goes down to 19 millikelvin.
Yeah, but still you are measuring an ensemble, right?
Yes.
Okay. And then what is the origin of Chi2 prime? What is the physical origin?
Of the susceptibility, you mean?
Of the imaginary part, yes.
Yeah, this is like the this tell us that your system is absorbing energy here. Yeah, it's like if you would perform a noise measurement, for instance, you will also obtain a peak. Yeah, at the same position where the peak in the imaginary part appears.
Okay. And in your next example, you showed quite different curves about the susceptibility versus temperature.
This one?
This one, yes. Maybe it's something basic, but I did not catch why is this so different.
Well, this here does not tell particular. Yeah, well, no, you are right, because these measurements by themselves does not tell at all that these nice effects of the CNOT gate are indeed taking place. I show them because it show very nicely that measurements performed in a in a 5-molecular layer, and measurements performed in a crystal exhibit the same results. To demonstrate that these spins are not collinear, what we did was to compare the equilibrium magnetic susceptibility. This is not equilibrium susceptibility. This was measured at different frequencies. But if you plot the equilibrium magnetic susceptibility against temperature, you see clearly the different regimes in which you can ascribe, for instance, to the system being thermally activated, to the system being antiferromagnetically coupled between them, or even reaching dipolar order between all particles. Okay, but oh yeah, sure, these measurements do not tell you that this is happening.
Okay, thank you very much. Thanks.
Thank you.
Okay, let me see if there are more questions. There is a question in the chat. And there is also a question. So first, Saulitius Vatikenas, can you please go ahead?
Yeah, thank you for the nice talk. It's quite interesting stuff. I was curious if you can measure magnetization magnitude with your techniques of, for example, a wire or a molecule. And if so, yeah, that's part number one. And if so, can you map it out spatially?
Yeah, so you mean if we can quantify the... Yeah, but we need to use also numerical simulations. I mean, we do that actually. This is, for instance, when I show you the measurements performed on the nanowires, this is what we did, and the results were quite good, by the way. We can, we only have the information, with the only experimental information we have is the amount of magnetic flux. And to translate that into magnetic units, we need to know precisely the shape of the particle and the position of the particle with respect to our nanosquid. Then we perform magnetic simulations, and we also simulate the superconducting currents flowing through the device, and we estimate how these flux units convert into magnetic units. But it's not fully experimental, as I told you. Yeah.
Got it. And
but
now
the results are, for instance, as you can see here, quite nice.
I see. And now,
the second question was?
The second question about the spatial, if you can resolve it spatially to some extent at least, let's say along the wire, if there is a domain wall and a flip of the magnetization along the wire, if you could tell the location of that.
Right now, this is very difficult because what we measure is the convolution of the signal of the whole sample. Ideally, what one would need to do is to be able of moving your sample, or to be able of moving your sensor, like in microscopy. For instance, the group in Tübingen, they are developing a squid microscope based on YBCO, and from my side, I am trying to develop techniques that allow me to in situ move the magnetic sample through the device. I'm working on that also. Yeah, the spatial resolution will not be as large as that of in the end it will be given by the size of the nanoloop, that is of the order of several hundred nanometers. So the best spatial resolution will be at best 100-200 nanometers.
Very interesting technique. Thank you.
Thank you.
Here is another question by Walter Arnold.
Yeah, thank you very much for your very interesting talk. I have a question concerning the tunneling of the magnetic moments, Chi2 prime. Where does the energy go to? Are these oscillations of the particles? So in a sense, acoustic Barkhausen noise in the individual particles?
Well, this is a very difficult question. We are not sure at all, because what we observed in these measurements was that the particles were indeed following the temperature of the bath. So this quantum tunneling process allows the system to be thermalized with the bath. But how this happens is still a bit difficult for us to understand. One possibility is that something we observe is that once the system is ordered by means of dipolar interaction, this mechanism dies out. So somehow the dipolar interactions do play our role here. So what we believe, is that this energy is dissipated to the bath through some kind of dissipation with, of course, phonons, because they feel the temperature of the bath.
If you would have a temperature sensor nearby, you might be able to measure the increase in temperature.
Yeah. Well, the molecules are indeed well thermalized. I mean, since they follow the Curie-Weiss law, we can determine their temperature quite precisely. But after this mechanism dies out, the system does not seem to be thermalized. In that case, it would be maybe nice to to be able to measure the temperature very locally. Yes.
Okay, thank you.
Thank you.
Okay, there is one question in the chat by Anjant Kumar Gupta. Anjant, can you please unmute yourself?
Okay, I will try. Can you hear me?
Yeah.
Okay. Thank you for the very nice talk and very nice work. I enjoyed it thoroughly, I must say. I have a question, which is like, you know, in conventional squids, I believe the best resolution is about 0.1 microphi-naught per root hertz. Are you right? I mean, so that, right, if you buy a squid from, let's say, Quantum Design, I think they will not be able to sell you anything better than this.
You mean the sensitivity of the squid itself? Yeah, 1
Correct.
microphi-naught per square root of hertz is quite a state-of-the-art value.
0.1. Okay, so that is the best you will get in the commercial or any conventional squids.
0.1 flux knot.
0.1 microphi-naught.
Yeah, microphi-naught. Yeah, well, this is already a quite good squid, I would say. Yeah.
I think what you are, I believe you are saying your resolution is better than this, no?
The noise we achieve at large frequencies is 50 nano-phi-naught per square root of hertz.
50 nano, right. So that is better than what is there in the conventional squids.
Yeah, also consider that that commercial squids do not exhibit, well, the sensitivity of commercial squid is not at all as large. Even though if the flux noise of the squid itself can be very good, then the coupling factor to the sample is always much worse. So you lose sensitivity through the coupling factor.
Right. I agree with you completely on that. Right. So you get much better flux, much better sensitivity in terms of spin sensitivity. But you are getting a better flux sensitivity also.
Yeah, but also keep in mind that this is also only true at very large frequencies, because unfortunately the 1/f noise of this device is quite large. This you can see here. 1/f noise is not is large in high TC superconductor.
So in this case, at low frequency, you have about a microphi-naught, and high frequency, you are claiming it is 50 nanophi-naught.
Yeah.
Okay. I think then it is, and any reason why you have this such large 1/f noise?
Yeah, well, this is typically ascribed to because of vortices in the high TC, and especially flips in the superconducting current through the junctions in the squid, and also we ascribe these high levels of flux noise to the presence of a spin noise in the device itself, maybe coming from the STO, very probably coming from the STO, although this is also observed in substrates growing in other oxides, but the spin noise is probably playing an important role. Yeah, it would be really nice to be being able of decreasing this contribution.
1/f, right. I think it's the same thing. You're right. Even in the conventional squid, it is blamed to the mostly spin noise at the interface, I think. Okay, great. Thank you. Thanks.
Thank you.
Okay, I don't see more questions. So if there are no more questions, so before thanking Pepa and closing the session, let me remind you that next week we have a talk by Juan Manuel Rodríguez Parrondo from Universidad Complutense de Madrid, and he will talk about scattering and thermalization, wave-particle duality, heat, quantum thermodynamics. So with this, I want to thank Pepa very much for her wonderful talk, and thank you all again for